Welcome back everyone. In this lecture we will continue with the study of finite dimensional representation of sln+1 C. So, we already proved the complete reducibility for these representations. So, to understand any given finite dimensional representation, we need to understand what are all the irreducible representations and their multiplicity inside the given representation. So, towards this we need to classify all the finite dimensional irreducible representations of sln+1 C. So, for that purpose we have actually developed this weight theory. So, we will continue with that and then understand more about the weights of given finite dimensional representation. So, let us start with V being finite dimensional representation of G. So, finite dimensional G module. Okay. So, we already seen that the action of H is semi-simple. So, this is the observation that we made, the action of H on V is semi-simple. So, in particularly we can talk about the weight space decomposition. So, we can write V as direct sum of V mu, mu comes from H star, where V mu is the simultaneous eigenspace. So, which is given by those vector in V such that when you act by H on that vectors, then you give that action by this mu of H for all H and H. Okay. So, we have this decomposition. So, we also have the weights. So, the weights of V defined to be those mu in H star such that the weight space corresponding to that is non-zero. Note that in the adjoint representation, the set of weights is invariant under the action of sln+1. So, that we have observed. So, very similar to that we can see that Sn+1 indeed acts on this weights of V as well for any finite dimensional representation. So, this can be proved using SL2 theory. So, what is the claim? So, claim is Sn+1 acts on weight of V. Okay. So, it is not just the action. So, we have moreover, so if we take some lambda from the weight of V, so then the dimension of this weight space is same as the dimension of this sigma lambda for each sigma in Sn+1. So, not only that Sn+1 acts on weight of V, the multiplicity is invariant under this action. Okay, that is what the second statement says. So, let us prove this. So, for this we need to actually invoke again the SL2 representation theory. So, let us actually recall. So, what is this SL2 copy for each I? So, for I coming from 1 to n, so we have this Si, so which is the span of Xi, Hi and Yi, where I range from 1 to n. So, this is indeed isomorphic to SL2C. Okay. So, recall that Hi is nothing but Ei minus Ei plus 1 I plus 1, and Xi is nothing but Ei plus 1, and Yi is nothing but Ei plus 1 I. So, these are all the elements. So, they are the Chevalier generators. So, now we can consider this sub-representation of V, call it V dash. So, which you take it to be direct sum of V lambda plus m alpha I, where m comes from integers. Okay. So, this is indeed SI submodule. So, that is something we have to check. So, if we take, so let us check the following. So, here is a small lemma. So, if you take any vector v in v mu and then if you act it by xi on that vector, then the way that vector must lie inside v mu plus alpha I. So, that means if you act xi on v, then the weight of that vector increases by alpha I. Okay. The weight of xi v increases by alpha I. And similar to that, if you apply yi on that vector, okay, for any of these vectors, then the yiv indeed actually the weight of that decreases by alpha I. So, the weight of yiv decreases by alpha I. So, that means this is lying inside v mu minus alpha I. So, modulo this lemma, it is easy to see that using this. So, this is indeed SL2 submodule. So, SL2, this SL2 copy that we are talking about, okay. This is the SI that I am talking about. So, let us verify this. So, this is easy to verify. So, if you take for any h in h and compute what will be the h action on xiv, then you can easily see that. So, you can actually commute this and then you can add the cost which will be given by the bracket hxi acting on v. So, hv is given by mu of v, okay. Hv is nothing but mu of hv. So, this is going to give you mu of h xiv plus h xi is 2 xi. So, this gives you 2 xiv. Okay. Sorry, this is hx, sorry, hxi is nothing but alpha I of hxi. So, because this xi corresponds to the root alpha I, okay, xi is indeed inside g alpha I. So, this is going to give you alpha I of h xiv. So, now if you rewrite this, then you can easily see that this is exactly equal to mu plus alpha I of h xiv. Okay. So, that means h acting on siv is giving you up to the scalar xiv, okay, and this is true for all h in h. So, that proves xiv is indeed inside this weight space v mu plus alpha I. Similarly, one can prove that the yiv will be inside v mu minus alpha I. So, that tells you that if you take this v dash, which is the direct sum of v lambda plus m alpha I, m range from minus infinity to infinity, that is integers. So, then that is indeed SL2 submodule. Okay. So, now let us look at this module very closely. So, this is the v dash, which is the direct sum of v lambda plus m alpha I, where m is running over integers. So, lambda is just say some fixed weight inside v. Okay. So, now we are looking at this SL2 copy, which is isomorphic to the span of xi, hi and yi. So, what are all the hi eigenvalues? Hi eigenvalues of this representation v dash are, so you take this weight and apply hi on that. Okay. So, this is just lambda plus alpha I on this hi. So, note that alpha I of hi is 2. Okay. Alpha I of hi is nothing but 2. So, because of that you get exactly equal to lambda of hi plus twice m, 2m. Okay. So, now you can easily see that for various m, this lambda of hi plus 2m, they are all distinct. Okay. So, there is no repetition of weights here. So, there is no repetition of eigenvalue. So, in particularly if this V lambda plus m alpha is non-zero, then the corresponding Hi eigenvalue is given by this lambda of Hi plus 2m. Okay. So, that is what we are getting. So, now if you look at what will be Si of lambda, that is nothing but lambda minus lambda alpha I, then look at Si of lambda of Hi. So, that is the thing that we are calculating. Then this is nothing but lambda of Hi minus lambda alpha I of Hi. Okay. So, this is exactly 2. So, if you do the computation, you can easily see that the lambda alpha I, if you write it in the epsilon I basis and then calculate, this is exactly lambda of Hi, because alpha I is equal to epsilon I minus epsilon I plus 1 and Hi is being EII minus EI plus 1 I plus 1. Then you can actually easily verify that lambda of Hi is going to be equal to the inner product lambda alpha I. So, that tells you that this is exactly equal to minus lambda of Hi. Okay. So, SI lambda of Hi is nothing but minus lambda of Hi. So, which is obtained by taking m to be minus lambda of Hi. Okay. So, that means this weight minus lambda Hi corresponds to the weight lambda minus lambda of Hi alpha I, which is nothing but Si of lambda. Okay. So, we already know from the SL2 theory, if k is a weight, that is eigenvalue of H, then the minus k also must be eigenvalue of H. So, there is a symmetric of all the eigenvalues of H. So, using that we can immediately conclude that. So, lambda is a weight, then that implies this lambda minus lambda of Hi alpha I must be a weight. So, indeed we actually proved something more, because we already know that. So, if you take this SL2 representation, the V dash k, if you look at the dimension of this, so this is going to be exactly equal to the dimension of V minus k dash, okay, because Vk is being the Vk dash is being the kth eigenspace of Hi. Okay. So, since there is this symmetric of Hi eigenspaces and the dimension of this Vk dash is same as V dash minus k. So, that actually tells you that the dimension of V lambda, which is exactly same as the dimension of V dash lambda of Hi, which is same as the dimension of V dash minus lambda of Hi. So, which is exactly equal to dimension of V of lambda minus lambda of Hi alpha I. So, this proves that the dimension of V lambda is same as dimension of V Si of lambda. So, now we conclude the general result by observing that these Si actually generates W or Sn plus 1. Okay. So, since Sn plus 1 is indeed generated by this Si's, we can conclude that the dimension of V lambda is same as dimension of V sigma lambda for all sigma in Sn plus 1. Okay. So, this indeed proves we have this Si of weight of V is subset of weight of V, and since Si being invertible, you can easily see that weight of V being finite set, this SI of weight of V must be same as weight of V. Okay. So, that is why we have this action of Sn+1 on this set of weights. So, Sn+1 acts on this set of weights. So, that is very clear, and it also preserves the multiplicity. Okay. So, this is somewhat very important observation that we have made using SL2 theory. So, if you are interested in understanding any given finite dimensional representation, so first we observe that we can actually have the action of H on this V. So, that is indeed semi-simple, and that gives you the weight space decomposition. Once you have the weight space decomposition, then we can ask this natural question, what are all the weights that are available and what will be the multiplicities. Okay. So, now we have observed that to understand the weight multiplicities, it is enough to understand the weights modulo this Sn+1 action, Sn+1 action. So, that is what we will be actually doing later. So, indeed we are going to prove that the data that we are actually getting it from this weight space decomposition. So, that is the set of weights and its multiplicities, that will be sufficient to actually say what is the representation. Okay. So, indeed that data determines the representation. So, what we mean by that, so to understand that better, we need to actually introduce what is called the character theory. So, let us actually define the characters, and then it will become clear what I mean by that. So, the characters merely actually kind of records the data that we were discussing about. Okay. So, if you start with the finite dimensional representation of G, and we know that the H acts on V semi-simply. So, then we can talk about the weight space decomposition. So, you take direct sum V lambda, lambda in H star. So, now what is the character of V with respect to the action of H, which is denoted by CH underscore H and V. So, which is the formal sum which actually encodes all the data that we are interested in. So, basically taking the dimension of V lambda times e power lambda, where lambda comes from H star. So, one way to think about it, you can actually think this as element inside the group ring or group algebra. So, you take the you take this H star. So, this is indeed abelian group. Okay. So, this is indeed a vector space over C. Okay. So, this is indeed abelian group. If we take this abelian group, and then we can talk about the formal sums, finite sums over this abelian group. So, you can talk about the group algebra generated by this H star. So, this is the group algebra generated by H star. So, indeed if you think about it, this group algebra has the basis. So, this is indeed span of, so because we are talking about group algebra over C. So, it is the span of, let us say, E lambda, lambda comes from H star. So, the product here, which is the addition of the vectors in H star, should be reflected in the algebra. So, that is actually kind of given by this exponential notation. So, if you take e power lambda, e power mu, so it is the convolution product. So, basically it gives you that e power lambda plus mu. So, basically the addition of the group is recorded here. So, that is comes from the multiplication of the algebra. So, now one can think this character as an element inside this algebra. Okay. So, now because this weights being the finite set, this is the finite sum, even though it looks like infinite sum, this is indeed finite sum. So, now what we are trying to say, if we know the character of V, then we know V. Okay. So, what we mean by that? So, here is the theorem, so which we will prove later. Okay. So, V is isomorphic to W as G module if and only if the character of V is same as character of W. So, one way is obvious, okay, this is obvious. So, because if two representations are isomorphic as G modules, then if you look at the set of weights comes from those two representations, they will be identically same and the weight multiplicities will be same, okay, that is why the character will be same. But for the converse, we need to actually work bit more. So, that is because the character is indeed actually possess very little information. So, we are using only the action of H, that is the carton, and then we are saying that so only the action of H information determines the G action. Okay, that is indeed very brave statement to make, and we are saying that indeed that is what happening here. Okay, the action of H kind of determines the action of G. Okay. So, in the sense that the action of H immediately tells you what are all the character. If we know the characters are same, then we know the representations are same. Okay. So, we will actually prove this later in couple of lectures. Okay. So, now once we define the character, then we can immediately ask the following question. Okay. So, there are this natural construction that we have already seen, the dual, direct sum, tensor product and so on. So, if we take the direct sum, what will happen and so on. So, let us actually see, it is indeed a simple exercise. So, if we take the character of V direct sum W, then that will be the sum of the character. So, note that we are actually working inside this group algebra. So, since it is a C algebra, so we have the addition, multiplication, everything there. Okay. So, what is the addition of the character? Maybe let me just explain here. If you write character of V to be the dimension V lambda e power lambda, lambda in H star, and the character of W to be the summation dimension W mu e power mu. So, maybe we will use the same lambda in H star. You can easily see that this e power lambda, this form a basis. So, this form a basis for C H star. So, because of that, the addition is just the coordinate wise addition. The character of V plus the character of W is given by the dimension of V lambda plus the dimension of W lambda e power lambda in H star. Okay. So, now it is easy to see that if you take the direct sum and then look at the lambda space, it is going to be the direct sum of the lambda weight spaces. Okay. This is easy to verify. So, basically this statement is same as this statement. So, now if you look at the dual, so the character of the dual, okay, since the weight of V star, we already know that it is minus of the weight V, and the dimension of lambda weight space is same as dimension of the minus lambda weight space of V. So, this tells you that the character of V star has this close relationship with the character of V. So, which is given by character of V star is equal to summation dimension V lambda star e power lambda, lambda in H star. So, now you just replace this by dimension V minus lambda. Okay, so those things are there, and then e power minus of minus lambda. Okay, lambda and H star. So, now basically what you are doing, so if you take these transformations, okay, from C H star to C H star, which comes from this linear map, lambda goes to minus lambda, then that can be extended to e power lambda goes to e power minus lambda. If you use this map, let us call it F, okay, then you can easily see that the character of V star is f of character of V. Okay. So, now if you go to the tensor product, then you can easily see that the character of the tensor product is just the product of the character. Okay. Again, this just follows from the fact that if you take the tensor product and then look at the muth weight space, then that is nothing but the direct sum of the this following individual space V gamma tensor W mu minus gamma, where gamma runs over H star. So, note that this is also same as the direct sum of V gamma dash or mu minus gamma dash tensor W gamma dash, where gamma dash again runs over V star H star. Okay. So, all these things are immediate from the earlier observations. So, one can actually see that, okay, as examples. The character of the natural representation is exactly given by e power epsilon 1 plus etc. plus e power epsilon a. Similarly, the character of the dual representation is given by e power minus epsilon 1 plus etc. plus e power minus epsilon. And thirdly, if you take the character of the adjoint representation, so that is given by, so e power 0 is like you can denote it by 1, so there is no harm in that, plus, so you take the summation e power alpha, alpha coming from phi. Okay. So, now it is not hard to see like how to compute, like for example, the symmetric powers on the alternatings and so on. Okay, maybe I leave it as exercise, compute the character of these symmetric powers sim2 of Cn, and then the character of alt 2 Cn. Okay. Okay. So, let us actually look at the action of G and then try to understand how it is reflected in terms of the weights. Okay. So, let us take again V being a finite dimensional representation of G, and then we fix this direct sum of this V as weight space decomposition. Okay. So, now we have this very special decomposition of G. So, as I already told, this is going to play very important role. So, this is called the Cartan decomposition or the triangular decomposition. So, now if we use this triangular decomposition and then see like how this action of this n plus n minus and h acts on V. So, to understand that, first we need to understand how each xi acts on the weight vector. Okay. So, let us make this lemma. So, if for h in h and of course, xi in n plus and let us say V is in V lambda, we have xiv is inside V lambda plus alpha. So, this is something we already observed, and similarly for yi in n minus and V in V lambda, we have yiv sits inside V lambda minus alpha. Now, if you take hiv, so this is going to be inside just the one dimensional space C. So, now take finitely many elements, okay, from the weight, from the root spaces. Okay. So, now we will generalize this to finitely many of them. So, now let us use phi for the roots and g alpha for the root spaces. So, now if we take some elements, let us say this is already one dimensional. So, let us denote the generated by x alpha. So, if you take x beta 1 etcetera x beta n, okay, for beta 1 etcetera beta n comes from phi, and then let us say h is comes from h and v is come from v lambda. Okay, then if you compute what will happen to this x beta 1 etcetera x beta n v, so that is indeed the weight of that. Okay. So, let us compute and see. So, this is going to be exactly equal to, so one can prove this by induction. So, this can be proved by induction. Okay. So, maybe I will do for n equal to 2 or something. So, if you take this, so since h acts as derivation, this is going to give you exactly x beta 1 etcetera x beta n. So, you can send all the way to the rightmost corner and then plus. So, it will give you x beta 1 the bracket times x beta 2 and so on x beta n applied on V plus etcetera plus x beta 1 times etcetera x beta n minus 1 h acting on x beta n applied on V. Okay. For example, if we take n equal to 2, so we have x beta 1 x beta 2 applied on V, you are applying h. Then first what you do, you just switch these two elements. Okay. Then you get x beta 1 h x beta 2 V plus, because you switched this, you have to pay the cost. This is h x beta 1 x beta 2 V. So, now again you switch these two. So, then see what you get. So, you get x beta 1 x beta 2 x V plus x beta 1 the bracket h x beta 2 applied on V plus x h beta 1 x beta 2 V. Now, you can generalize this using the induction. Okay. Then you will get this formula, and this formula tells you that. So, this is exactly gives you the weight lambda of h. Okay. This corresponds to lambda of h, and this you get beta 1 of h, and here you get beta n of h. So, indeed this is exactly equal to lambda plus beta 1 plus etcetera plus beta n of h times this x beta 1 etcetera x beta n applied on V. Okay. So, indeed what we proved, so x beta 1 times etcetera x beta n times V sits inside this weight space V lambda plus beta 1 plus etcetera plus beta n. Okay. This is what we indeed proved. So, we will use this later and then try to understand actually how typical element in G acts on capital V using the PBW basis. So, we will do that computation in the next class. We will stop here.